Let's start with oil flowing through a long pipe. Example 8.2. We are given pipe length L equal to 330 meter and the diameter is 0.28 meter. Oil velocity is given 0.5 meter per second and the density of water is 894 kilogram per meter cube. And lastly, dynamic viscosity is 2.33 kilogram meter second. Our goal is to find the pumping power required. Step 1. First, we calculate the volume flow rate by equation V flow rate equal to V pi D squared per 4. So we substitute the values and we get 0.308 meter cube per second. This tells us how much oil flows every second. And next, we identify the Reynolds number. The Reynolds equation is rho VD over dynamic viscosity. So we will get 54. Since this value is much less than 2300, the flow is laminar. Next, we would like to find a friction factor for laminar flow. The equation is F equal to 64 per Reynolds. So we substitute the value Reynolds, which is 54, and we will get 1.19. As we get the friction factor, we substitute into the delta P, which is F LD per rho B squared 2. So we will get 156.9 kilopascal. This is the pressure the pump must overcome. And next, we will find the pumping power, which is work pump. So we substitute the value and we will get 4.83 kilowatt. And the pump must supply 4.83 kilowatts of mechanical power. Next, for example 8.7, it is a different but a related situation. A pipe that gradually expands and the value given is diameter. Diameter increases from 6 cm to 9 cm. Upstream velocity, which is 7 meter per second, and the pressure also upstream, which is 150 kilopascal, and the loss coefficient is 0.133, and the water flow is horizontal pipe. Next, we would like to get a head loss. We use the equation coefficient loss times V velocity power of 2 minus divide by 2G, G which means gravity. The value is given 0.133 times 49 divided by 19.62. So we will get 0.333 meter. This is the energy loss due to the turbulence. And lastly, we apply the energy equation, which are P2 equal to P1 plus rho g times alpha 1 V1 power of 2 divided by 2g. Value given, and we will get P2. We will get 168. This result highlights a critical concept, which are if the velocity decreases, the pressure point increases. Some energy is lost, but the pressure is recovery from slowing flow and is larger than the loss. That's why pressure can rise even when losses exist. To summarize these two examples, for example 8.2, it shows that how friction causes pressure loss that must be overcome by a pump, and the example 8.7 show how velocity changes can convert into kinetic energy into pressure. And together, this example demonstrate how energy is added, lost and transformed in pipe flow system. Thanks for watching.